Welcome to this seminar with Kilian Risse from KTH, Royal Institute of Technology. Kilian is working on proof complexity, has been working on proof systems like resolution and polynomial calculus and higher up in the algebraic hierarchy, and he will tell us about some of this work today, in particular a problem that has been open for quite a while, a stubborn problem on hardness of matching formulas. So Kilian, please, without further ado.
Okay, hi all. I will talk about the paper that we posted a few months back, and I was so lucky to work with Per on this. Okay, yeah, if you have any questions, please interrupt me at any time. So now the problem started. I cannot move to the next slide. Here we go. Now I can. Good. So what do you want to talk about? We want to talk about perfect matching, and namely about the problem whether such a graph has a perfect matching. And right, we can try, but somehow always one vertex is left alone. And this is, well, this graph clearly doesn't have a perfect matching just because it has an odd number of vertices. And I mean, the natural problem is to ask, well, how hard can this be for proof systems? And what I want to talk about today, or what I want to show to you, it's that this is actually a pretty hard problem. Okay, but yeah, so let's first take a step back. And so what do we want to talk about? We want to talk about proof complexity, which is somehow the study of certificates of unsatisfiability. So for example, could you provide me with a proof or a certificate that the following CNF here is unsatisfiable? And the initial motivation for proof complexity is like trying to separate NP from conp. But we are like far from this. We don't know how to prove this. And so instead we focus on concrete proof systems, like with restricted deductive ability, in order to prove meaningful lower bounds on the length of these certificates. In this talk, we'll talk about sum of squares, but feel free to like plug in polynomial calculus or bounded depth Frege. Like the results that I'll talk about, unless explicitly specified, work for all three proof systems.
And do you get exactly the same results, or you need some obvious modifications, or I should
say some obvious modifications.
Okay, but morally it's like the same.
Yeah, morally like you get the same results.
Okay, thanks.
Okay, so yeah, I mean, let's define sum of squares. So the sum of squares is a static semi-algebraic proof system, meaning that somehow the certificate or the proof that we obtain is just a single polynomial, or like a polynomial identity. And so somehow the name of sum of squares stems from the fact that SOS is actually aware that squares are non-negative. So suppose we're given a system of polynomial equations, which you would like to simultaneously satisfy. So we want to find an assignment to the variables so that each polynomial is set to 0. Then an SOS certificate of unsatisfiability of this system of polynomial equations is a sequence of polynomials so that the first few polynomials can be multiplied by the corresponding axiom and then summed up. And plus we can add the second part of the sequence squared so that we obtain like the polynomial -1. And clearly, if we have such an identity, then the system of polynomial equations is not satisfiable. So why? Well, if we look at the left side of this equation, this would be a positive number, right? Because ti times pi's, like the first sum would be equal to 0, the second sum would be positive, but this is equal to -1, which can clearly not be, and therefore we don't have a satisfying assignment. Okay, so then what is like the main measure that we're interested in is like the degree of an SOS refutation, which is just the maximum degree of any monomial appearing on the left side without cancellation. And then the SOS degree of refuting a system of polynomial equations is just the minimum degree of any SOS refutation. Okay, any questions about SOS? I believe this is fairly standard. Good. So then we want to look at the perfect matching principle and like write out or spell out how to actually code this. So for each edge in our graph, we want to introduce a Boolean variable with the intended meaning that if it's set to 1, then it's actually in the matching, this edge, and otherwise it's not in the matching. And then for every vertex, we want to ensure that somehow exactly one edge incident to this vertex is set to 1, because we want to obtain a perfect matching. And yeah, as I said before, we assume that these edge variables are Boolean, and therefore we have to include the Boolean axioms. Good. So what do we know about the perfect matching? So first, somehow, a positive note is that, like, for a solution in various settings, we actually know that this is a very hard problem. And I don't really want to go into the details, but rather want to focus on SOS. And there we actually know that if the graph G is bipartite, then this problem is fairly easy to detect, assuming that we have an odd number of vertices, and therefore it's unsatisfied. SOS can in fact refute such formulas over bipartite graphs in constant degree. On the other hand, we know that there are sparse graphs that are hard for SOS. And
Kilian, just sorry to interrupt you, just a question. So this constant degree, what does it depend on? Is it like just fixed constant, or?
It's a fixed constant, like
fixed constant.
8, 6, or 4.
Okay.
I don't remember. So somewhere
Great.
there. Yeah.
Okay, thanks.
Okay, but yeah, as I said, on the other hand, we know that there are sparse graphs, so that SOS actually requires linear degree to refute this formula. Okay, and then there was this explicit open problem by Razborov, who asked whether, given a deregular random graph, like this is the notation that I'll use throughout the talk here, like this G according to G and D, this means that we sample a graph G as a deregular random graph. And he asked, Razborov asked, whether Lovász-Schrijver requires a polynomial in n degree to refute the perfect matching principle on such regular random graphs. And so I don't want to define what Lovász-Schrijver is, but it suffices to know that SOS in degree D can actually simulate Lovász-Schrijver of rank D. So yeah, sorry, it should say Lovász-Schrijver requires rank n to the delta. But yeah. Okay, and so our results are actually is a theorem of this type. So we show that if you sample a graph G as a random regular graph for where the degree of each vertex is a large enough constant, then with high probability SOS actually requires degree n over log n to refute this formula. And let me also mention some other results. So we also have a similar theorem for the even coloring formula, which is basically the perfect matching formula, but instead of matching each vertex once, we match it like degree over 2 many times. So like half the edges incident to every vertex are set to 1. And there, again, we get like the same kind of lower bound of degree n over log n. And these two theorems, as I mentioned earlier, also hold for polynomial calculus as long as we are over characteristic different from 2 and bounded depth Frege. So we really need to require that we're over characteristic different from 2, because otherwise you can relax the perfect matching principle over an odd number of vertices to the Tseitin formula, and the Tseitin formula you can just refute by Gaussian elimination over GF2 in polynomial calculus. Okay, and then, yes?
So but is it obvious that you could relax any perfect matching instance in that way, or could it be like if you have for the if all the whole violation witnesses somehow have, you know, Or wait, you don't, this is not even bipartite. Yeah, how does it, like, is it, if the graph doesn't have an odd number of vertices, is it clear?
You're skipping ahead to the open problem section.
Okay.
But yes, this is an excellent question. So in particular, are there graphs that are hard for polynomial calculus over GF2? This is not clear whether this exists.
And is it clear that you need to lose a log in the lower bound?
No, this is, yeah. No.
Okay.
Why did I say something?
No, I'm just
Sorry,
curious.
okay.
If the big
Yeah.
omega n over log n is just curious whether you could, I guess for the worst case examples that you mentioned, you would get the linear lower bound.
Yes.
Yes.
I would like to have a linear lower bound, but
Okay.
I don't know how to prove this. Yes.
You take what you get.
Yes.
Fair enough.
Okay. Good. And yeah, so we have one more theorem, which is a bit of a different flavor, and it discusses or is about polynomial calculus space. And here we improve upon like previous results, which had a square root n lower bound, and now we have a n over log n lower bound on the space required to refute the Tseitin formula over an alpha expander, where the average degree is again a large enough constant. Okay. Any questions about the theorem statements? Except if you don't know what polynomial calculus space is, then I don't want to define this. But okay, good. So I'll not talk about the second and third theorem, like at least in the first part. We can discuss this later, but let us look at the first theorem. So what is the main idea of the proof? So the main idea is to somehow embed these worst case instances that I mentioned earlier, like these sparse worst case instances for perfect matching, into a random irregular graph in such a manner that the hardness is preserved. And so what does this mean? What do we have to ensure in order to preserve the hardness? So let us look at some graph, and let us assume that this green graph is really a hard graph for SOS. And now let's embed this into a bigger graph, right? And then could it be that this bigger graph is now actually hard because it has this green hard graph as a subgraph? Well, I mean, in this example, we have isolated vertices. So clearly this cannot be hard because you already have contradiction in your axioms. So clearly we don't want isolated vertices, and maybe this explains why we discussed like deregular random graphs instead of like Euler-Schrijver random graphs where we would expect isolated vertices to show up. Okay, so let us remove the isolated vertices. These were somehow a silly thing. And now, what is a property that would be desirable? Well, if I could wish for, then I would like to have a perfect matching on the outside, like on vertices that do not participate in this green graph, right? Because then we could like restrict the remainder away, we would satisfy all the axioms, and we would be left with this hard instance. So in particular, we don't want vertices looking like this because we cannot match them to other vertices that do not participate in this subgraph, in this hard part of the formula. But like a graph like this would be really cool because now we can set the edges that I marked orange to 1 and all the black edges to 0, and we would somehow be left with the hard instance, and then we could like apply the lower bounds for this green instance that we assume exists. Okay, but now one last step is somehow to realize that, that I don't want to look at this hard instance in a lot of detail. But this could be like locally, for example, very dense, and then you would not really expect to find this graph as a subgraph in a random deregular graph. So instead, we want to somehow find a bit an uglier version of this hard graph, namely where every edge, instead of remaining a single edge, is now a path of odd length. And why do we want odd length? Well, like this, if we have odd length paths and you like propagate 0, 1 along these paths, then somehow it behaves right, and it behaves like the perfect matching formula over this green graph. Okay, good. So yeah, do you have any questions at this point? Yeah. Okay, so what is the proof sketch? Well, we want to embed sparse graph H into G, and in such a manner that the edges of H are mapped to odd length paths, plus there is a perfect matching on the vertices that are not in the embedding. So then if we have this, then we can set the edges in the matching to 1. All other edges that are not in the embedding, we can set to 0. And then by like restricting the original formula over G by this restriction, then we're left with a formula that behaves kind of like the perfect matching formula over the graph H. And therefore, like the degree required to refute the perfect matching formula over G is at least the degree required to refute it over H. Okay, good. So now, yeah, so how do we implement this idea? We chose like a two-step approach.
So Kilian, just to check, so maybe you said this already, but here we're using that all of these proof systems, both the one you're telling us about and the ones you're not telling us about, they behave nicely when you hit the formula with a partial assignment, right? When you hit it with an assignment and simplify it, the formula can only get simpler.
Yes.
And
exactly.
this, okay, good.
Yes. Yes. Okay, good. So yeah. So how do we implement this? Well, we chose a two-step approach, where in the first step we somehow split the original graph G into two large parts, and where then on one part we do somehow the embedding, and the other part will then be used to ensure that there exists a matching. So let us look at like an example. So we want to split our graph into two parts. The lower part is the set T, which will be the part on which we want to do the embedding argument. So we actually want to find a hard instance like on the graph induced by the set T. And the crucial property that we want is that no matter what odd-sized subset of T we remove from this graph, we have a perfect matching on the remainder, right? So if we remove this set U, which has an odd number of vertices from the graph, then we actually have a matching on the remainder of the graph. And this should hold for any set U. Okay, and this will be the first part, and then the second part will be to like embed the graph in this G of T, like the T-induced graph of G. And because it will like be an odd number of vertices, or this embedding will consist of an odd number of vertices, we can then apply this property, and then we're done. We have actually what we want. Okay, so let us see what we actually can prove. So we prove this partition lemma, where we say that if we sample G as a random regular graph for again, like a large enough constant degree, then with high probability, there exists such a set T, so that it is fairly large. And we can embed the worst case graph into the T-induced subgraph of G. Plus, we have this important property that if we remove any odd subset of T from G, then G minus U has a perfect matching. Okay, good. So let me mention how you prove this. Like the main proof ingredients, somehow the Lovász-Schrijver lemma, to ensure that somehow every vertex has a large neighborhood not in T. And then from this, you can show using Weyl's theorem plus Cauchy's interlacing theorem, you can show that you have control over the spectrum of this graph G minus U. And then from these like control over the spectrum, you can apply like known results to conclude that there will actually be a perfect matching. So that's somehow the rough sketch of how the proof of this lemma goes. Okay, any questions?
So the graph is like super close to having a matching, right? I mean, do I get it right that any single vertex that you remove, you're going to be able to match all the rest? Is that right? Because you could have size like 1.
Yes, as long as it's a subset of T.
Yeah. Okay.
So yeah. Okay. So this is our partition lemma, and now we have our embedding theorem. So what does this say? This says that if we have a graph G, which is a constant degree alpha expander, where alpha expander means like a vertex expansion on n vertices, and it contains somehow many odd length cycles, which are fairly short, but not too short. I don't want to formalize this like exactly, but if G satisfies somehow these two properties, then and H is not too large a graph, so it's like it has like n over log n many edges, and the maximum degree of H is upper bounded by the average degree of G plus some constant dependent on alpha. And then you can actually find H as a topological minor of G, or like spelled out like you can find an embedding of H in G so that each edge is replaced by an odd length path, and these are pairwise vertices, right, except in the endpoints. Okay, good. So with these two, like this lemma and this theorem, we can now actually prove our main theorem. So first we apply the partition lemma, then we embed the worst case graph H into G of T. This embedding will have an odd number of vertices, so we can remove these from the graph. We can apply this property from the partition lemma that will have a matching on the outside. We can restrict all those vertices away. The remainder behaves like the perfect matching formula over the graph H, and therefore SOS requires omega of n over log n degree to refute the formula over G. Okay, so this is the proof outline. Let me check the time. Yeah, so now I like somehow want to go a bit into technicalities and show you how one would want to embed a graph into an expander. Yeah, so let's see how this goes. So first, I want to look at a simple example which somehow illustrates the main points, and then from there we will like generalize it as far as we get in this first part. Okay, so suppose we have like this short cycle, or like this cycle on 6 vertices, and we would like to embed this into this big graph. We want to maintain 3 sets. So we have the black set, the blue set, and the red set, where we can think of the black set as the part of the graph that we want to work on. The blue set is what we have embedded so far, and the red set is like the trash. So whatever we don't know what to do, we move it there. Good. So we proceed like just naively by picking a vertex in our small graph H that we want to embed and identifying this vertex somewhere in this big graph, then moving it to our embedding. And once we have done this, we want to clean up our big graph so that it's expanding again, because this seems to be a useful property. So we, in particular, like this one vertex here, like this guy, this is very not expanding, so we move it to the trash. Good. So we continue in this fashion. We pick another vertex, we move it to our embedding, then we clean up the graph, remove any non-expanding vertices or any set of vertices that is not expanding. And then now we want to find a path between these two vertex embeddings. And we'll take a path through this black graph, like through the part that we're working on. And because we maintain that this graph is always an expander, we kind of know that this path is fairly short, namely of logarithmic size, right? As long as you have neighbors in this graph. So we can do this, right? We can find a short path connecting these two vertices. So now we can continue and pick this vertex and identify something over there. And now we already see that we're somewhat in trouble because this vertex that we picked only has degree 1 in this original graph. So clearly we cannot complete the embedding. But let us continue. So what do we do? Well, we pick another vertex. We try to, we move it to our embedding, and now we want to connect these two, but we can't, right? But now what we'll do is we'll just move or unembed this previous vertex, the third vertex, move it to the trash set, and then try again, okay? So and then try again, and everything works out. And we continue in this fashion until we either have an actual embedding, we actually have found like our desired embedding, or at some point our trash set gets too large. Namely, it's larger than a third, like 1/3 of the entire vertex set. And now we want to argue that this can actually not happen. We'll never end up in this case where the trash set gets so large. So why can this not happen? Well, the argument will be that we started with an expander, and it turns out that expanders don't have small balanced separators. So think of a balanced separator as a set of vertices that somehow separates two large chunks of the graph. Because there are, yeah, and then the neighborhood of our trash is small because it's not expanding into C or into this reservoir of vertices. Plus our embedding will be small, so somehow it's going to be too small than what you would want. I don't know, I think I messed up this explanation. Do you have questions? Or?
So when you throw things into the trash, you will, I mean, there will be no other paths from the red part to the black part except through the blue part. That is somehow part of your cleaning up operation.
No. The red part may have neighbors in the black part, but not enough neighbors. Like it's not expanding, and therefore we removed it, right?
I just mean, what's this notion of a separator? What does it mean that this, because you run into a contradiction if this blue set somehow separates the red from the black and they're both too big, or no?
No, it's the neighborhood of the red set in our black set. So yeah. Those green vertices plus the blue set.
Yeah.
This will be our balanced separator, and it separates the red set from whatever remains in the black set that is not a neighbor of the trash.
Okay, thank you.
Okay. Good. So, okay, so let us try to formalize what I just said. And yeah, maybe I should mention that the main proof idea is due to Krivellevich and Nenadov and not by us. Okay, so right, we want to embed H in G. And what do we start with? We have like these three sets. We have the trash set A, we have our embedding that is in the beginning empty, plus we have our reservoir C. Now, we pick a vertex in H and we want to embed it. So we choose some vertex in C, remove it from C, and add it to our embedding. Then we restore expansion in the induced subgraph by C by moving non-expanding sets of vertices to A. Then we want to connect our new embedded vertex to previously embedded neighbors, right? And if this is not possible, if there is a neighbor so that we cannot connect it by a path to this neighbor, then we remove that neighbor to the trash set. And then we stop once A gets large, or we actually have an embedding. And the argument will be that the neighborhood of A in C plus the embedding is small, and it will be too good a balanced separator. And therefore we'll obtain an embedding of H in G. Okay, do you have questions? Or I can never decide whether I'm going too slow or too fast on these things. So I don't know.
I think you might be, but I'm still interested. I mean, so you could imagine that this embedding theorem would somehow work with high probability or something, but you're actually making a stronger claim. Are you? You're saying that, I mean, the probability is obviously over the random graph, I guess, but if, no, it's just an expander. So this is like an absolute statement. There's no probability here.
Yes.
That's interesting.
The only thing that we use is that n is large enough.
Okay, interesting.
Yeah. I mean, if you have seen like proof complexity arguments, like using a closure, this seems to be like very similar in spirit somehow, the argument. Okay, good. So yeah, so let me define what a balanced separator is. Or what notion of balanced separator we use. So S in G is a balanced separator if you can partition the vertices of G into 3 parts, A, S, and B, so that all edges from A go into S and all edges from B go into S, and there are no edges between A and B. And we also want that A nor B is the entire graph. So both are bounded in size by 2n/3. And then, like a straightforward lemma that one can prove is that if you have an alpha expander, then S is fairly large. Namely, it's like of size alpha times n divided by 3 or 4. Okay, so with this knowledge, I can actually refine the previous proof outline. So let us try to like actually make this more concrete. So now what do we assume? So in the beginning, we assume that we have an alpha expander. We set beta to this constant that we saw in the previous lemma. And we want to ensure that G of C is actually a beta expander. So it's not an alpha expander anymore, so it gets a bit worse, but we still maintain some kind of expansion. And then, yeah, we do everything as before. And in the end, we want to argue that our set, the neighborhood of A in C plus the embedding of H is actually less than beta times n. But now we can see that this is kind of true, right? Because once we stop, you can actually show that A is not larger than 2n/3. So we know that A is like upper bounded by 2n/3. But then we also know that everything in A is not expanding into C. So then we get that somehow the neighborhood of AC is definitely less than beta times n, right? It's a constant fraction of this. And now if we choose H small enough, assuming that we have somehow control of how large this thing is, then everything should work out, kind of, okay? Okay. So, yeah, let us actually look at whether or not we have control over this embedding and how large this embedding may grow. So recall from before that we sometimes get into a position where we have to remove like embedded vertices, right? Like here, we had to remove this vertex because we couldn't connect it as we wanted to. But now there is like a slightly subtle issue, namely like there is this edge embedding here, like this edge that we had used before, which we cannot move to A because it's expanding, right? But we kind of would like to. And now, if we do this process of embedding and unembedding like many times, then these paths here may grow very long, and therefore we lose control over the size of the embedding. So somehow we want to prevent this, and like the obvious solution is to remove the vertex plus the incident edge embeddings, or at least try to do this, right? We don't just want to remove the vertex embeddings once we have a problem, but we want to remove the edge and the vertex embeddings. Okay, so what do we want to do? Like anytime we get a conflict, we want to remove the vertex embedding plus the incident edge embeddings. But the issue is, as I try to elaborate, that some vertices we now want to remove may still be expanding into G of C. So, and if we have this, then we cannot argue that our found separator is actually small, or our found balance separator. But somehow the main observation is that as long as you can ensure that only a small fraction of A is expanding, then you can just add this small set to your balance separator, and you're still fine. Right? Okay, so what is the main idea here? So instead of embedding each vertex as a vertex in G, we actually embed each vertex as this flower or star-like structure here. So we still have like a vertex, like a unique vertex in the middle, and then we have these branches which are fairly large on each side. And I mean, intuitively, this is like a nice structure because it gives you many options to somehow connect this one vertex to other vertex embeddings, right? And then now I get into the details, but like you have to choose these branches fairly large, namely of logarithmic size. Plus you want the degree like to be a bit larger than the degree of the vertex that you're actually embedding. Because at any point, whenever you want to unembed this vertex or remove it to the trash set, then you somehow want to argue that you have a large set, this red colored set, which is not expanding, right? And if this is large enough, then you can somehow ensure that only a small fraction of A is expanding. That's somehow the intuition. Okay, so we can refine the embedding like outline once again. So now, what do we do? Well, we maintain two trash sets, A plus A prime, where we want to maintain that A is not expanding, plus A prime is small compared to A. And every time we embed a vertex in H, we actually choose a cross, like this is this flower-like structure that I showed you before, and remove it from C. We again restore beta expansion, connect E of V to the previously embedded neighbors. And then if some neighbor we cannot connect to some neighbor, then first we move the non-expanding part of this vertex to A. We move the expanding parts to A prime, plus all the incident edge embeddings to A prime. And because these edge embeddings are fairly large, or well, yeah, they're like roughly, they may be of size log n because they're like upper bounded by the diameter of G of C, right? So this is the reason why you want these branches of this cross to be fairly large. So they can like counter the size of these edge embeddings. Okay, and now, yeah, again, we stop with A is large, and because A prime is small, like we can still do the same. Good. Now I'm almost done with my presentation, and let me like just remark a few things. In this second step, we want to actually use, like we have to argue that such a cross actually exists in G of C, right? And for this, we actually need like a separate embedding argument. It is exactly the same, but you somehow have to prove it twice, which is a bit annoying. And also something further that I have not talked about yet is that we want that the parity of the paths connecting to vertex embeddings is odd, right? So as like a last thing, let us quickly discuss how that goes. And after that, I want to conclude at least the first part of this presentation. So yeah, so what do we want to do? Well, we have these two vertex embeddings, the vertex embedding of U and the vertex embedding of V, with these different branches here, right, as drawn as like these circles here. And we want to connect two of these through G of C. And now we want to ensure that actually the path from here to here is like of odd length, right? this path here should be of odd length. Now we just, like, I guess we do the obvious thing. We just ensure that G of C, because it will always remain a fairly large part of the graph G, actually contains odd cycles, which are not too short, but not too long either. And that we can actually connect one of these branches to like one vertex, and to a different vertex we can connect a different branch. And once you have this, you can clearly choose the parity, right? You can either like route your way here or here, and you get odd length paths. Good. Yeah, so this argument requires some care. We can discuss about it more later. I really like this part of the argument, but I have not been able to get very excited about this part. Yeah, anyway.
Is it clear why you said that you don't want the paths also to be too short? Why would you? I mean, like a triangle would look great.
Yeah, but I mean, all we can guarantee about the triangle, all we can guarantee is that we have alpha expansion, right? Now, this means that it could be that this triangle is just connected by a single edge to the rest of the graph, right? Like if alpha is not huge.
So do you want the cycle to be somewhat large in order to have a decent chance to hit it? Is that what you're saying?
To actually have two vertices that are connected to the rest of G.
Okay.
Right. Like it should be like of length 1 or 2 over alpha or 3 over alpha. So that you have a few vertices that are connected to the rest of the graph.
Okay.
Does it make sense? Good. Okay. Good. Yeah. So this is all I want to say in this first part. So what did we show? We showed that random deregular graphs, the perfect matching formula defined over these are hard for SOS, as long as the degree is large. And let me just mention 3 open problems. One is that like our degree required is somewhere around 150,000. Even though we haven't tried to optimize this, I don't think you get away with much less. Can you do better? Another thing is obviously what Jakob already asked, whether we can get linear lower bounds instead of this n over log n. And a third one, which I really like, but I don't know how to prove this, is whether or not there are graphs G so that the perfect matching formula is hard for polynomial calculus over G of 2. So in particular, this cannot be graphs on an odd number of vertices, and also it cannot be graphs that are bipartite. But yeah, I have no idea whether or not this is true, but I like this question. Yep, that's all. Thanks.
Thanks a lot. Again, applauding on behalf of everybody. And the floor is certainly open for questions. We do have time for questions, after which we'll have a break, and then we'll reconvene for a second technical half, those of us who wish to do so and have time. But I certainly have a couple of questions, but I thought I'd give the rest of the audience a chance to ask questions first, maybe. Or maybe I'll just ask my questions while the others are thinking. So like another perhaps vague open question is would this be useful for something else? Because you have it's interesting that you get like a worst case to average case kind reduction, or is the reduction in the other direction? I can never, I guess it's like an average case to worst case, whatever. So because, and I guess for sums of squares lower bounds, it's fairly standard that you do something that in the end you end up with the hardness of Tseitin. But like for other proof systems like polynomial calculus, I think it's more, we don't have that many reductions, and certainly it's not so common to do average case to worst case reductions. It's more like people tend to prove lower bounds with their bare hands. So could you use this machinery to maybe attack other formulas for which we don't have lower bounds?
Well, I mean, there is one formula that I thought about briefly, and that's coloring, but this doesn't work. And the main reason is that random graphs locally are too sparse to somehow force colors of vertices. Or at least I don't know how to do this, but like each edge would somehow have to force colors of two vertices, right? Or the edge embeddings, or whatever. And for this, you need a fairly dense graph. But in order for this to be small, it just doesn't work. I don't think this is useful. I don't know any other problems that are interesting. Yeah.
Thanks. And what do you think about this constant? That, I mean, did you think you can shave off a 0 or 2 at least, or like, or what's like the? Can you say something about what the bottleneck is? Do you think this machinery could just hit it harder and be smarter? You can do something, or you need another idea, or?
Okay, so our the embedding theorem has a constant of somewhere around 500, like in the degree parameters, whatever. There is like some constant of 500 around. That one I did not even try to optimize. I think you can get down to a fairly small constant if you would try. But then we need this partition lemma, which requires, which uses the LLL, the local lemma. And there we use a Chernoff bound, and in order to use that, we need that the degree is rather large, and somehow that is the main bottleneck. So if you could like replace this partition lemma with something else, you might get away with a lower degree, but I don't know how.
I see. I guess it's the final chance to ask questions before the break. And if we don't have any questions, then we'll just take a 10-minute break, and we'll be back something like a minute or two after 3 p.m. Central European Summer Time, daylight saving time. So we're taking a break now. So we're back after the break and have been discussing during the break what technical details to do. So now Kilian will tell us what the decision is, I guess, and get started on it.
Okay, so that is improved the last bit of that I haven't shown you yet, and this is this partition lemma. And I just like, because I'm allowed to be technical now, I just want to have the formal definitions, and they're not so hard to understand. So the first part is that we want max degree robustness, which is just saying that if you look at a linear sized subgraph, then you want to find a vertex in there with high degree, right? So for any subgraph on size at least kappa times n, the induced subgraph should have like maximum degree larger than d. So this is max degree robust, and I guess you can see why this is useful, because if you like want to embed these crosses, then you want to find this one vertex which has high degree, right? And yeah, good. And the other one is this odd cycle robustness, where again we look at sets of linear size, and we want to find a cycle C which is size at length at least L, not at most. At least L, and it's upper bounded by this 2 times the diameter of GFU plus 1. The upper bound is really uninteresting. This is like immediate, because if you ever find an odd cycle, then you can always reduce it to a cycle of this length, but somehow the lower bound is more interesting. So in some sense, you don't have 2 short cycles.
Kilian, since you're giving us these formal definitions, do you want to tell us a little bit how to think about the parameter? I'm still thinking about this max degree robust thingy.
Oh, okay. So you can think of kappa as like 1/3. It's a pretty safe choice. And d here should be like the maximum degree of h times 1 over alpha squared, I think, if I'm not mistaken. So somehow, right, these crosses that we embed for each vertex have larger degree than h has, right? And it's somehow by a beta factor larger, which is at most like alpha squared, or which is roughly alpha squared.
But the size of U is like linear.
Yes.
So it's very large.
Yes.
Okay.
Yeah, I mean, yeah, these definitions are not very interesting. Like they're just they work. Like I don't think there's anything going on.
No, but okay. So so please say again just what you use it for.
So the max degree robustness is used to actually find a vertex of high degree so that we can find the cross, right? Remember this, like each vertex we embed as like this flower or star-like thingy, where we have like a high degree vertex, which is connected to large branches, right? Looks something like this. And all these branches are vertices, right?
And you just need to argue that somewhere in what remains, you will be able to find such a vertex.
Yes, exactly.
Okay.
And what remains, like this kappa, it's always like a constant fraction of your graph. Because otherwise A is too large, like your trash set.
Okay.
Okay. And yeah, the odd cycle robustness, I guess we figured we know where to use, or just to make the path solved. Okay.
Yes.
Good. So then we can actually look at the partition lemma. Yeah, so as I said, like, let me draw a picture. We have our graph, we split it into two, S and T, and on T we want to actually run the embedding argument. So what do we want? We want that T is large. We want that G of T is an expander, right? Because this is what we need for the embedding. We want it to be somehow odd cycle robust with some parameters. We want it to be max degree robust also. Okay, and then again, we have this for all you, like this perfect matching thing. Good.
So, but technically speaking, that means that the partition lemma is actually not only using expansion, but also to a certain extent randomness, is it?
Yes.
Like properties 3 and 4 would not hold just because the graph is an expander necessarily, or would they? Or it's unclear.
This one I do not know. Like I tried. I don't know whether it holds for spectral expansion. Whether spectral expansion is enough. It's for random graphs. It's enough. I think this one holds also. This one just uses the mixing lemma. So this also holds for spectral expansion.
Okay, so expansion might be enough. We just don't. But
yes.
Okay.
But for this we currently use randomness.
Okay.
Yes. Okay. So then let's see. So yeah, we want to make a good cut in our graph, and this will be a degree balanced cut. And so we want a partition S and T, and we have a parameter C and epsilon, and we want that the set S is roughly C times N of the graph, right? It's like a constant fraction. And we want that for every vertex U, at least like it has a large fraction of its neighbors in S. So at least C minus epsilon fraction is in S, and C plus S, or up to C plus S epsilon. Yeah, you can also. So somehow we want the graph to be cut as it's expected, but also for every vertex, the neighborhood is split as expected. Good. Did you parse the definition?
So far, I'm happy.
Good, great. Okay, and now, So the first step is to show that actually every deregular graph has such a degree balanced cut. And then in the second step, we'll actually show that if you have a degree balanced cut on your home, then we have all the properties that we want. So first, showing that you have degree balanced cut, it's really an application of the local lemma, and we're done. So let us see how this goes. So we place every vertex of U into the set S with probability C. So then by turn-off, we actually have the required size, right? And now we want to ensure that every vertex has like the expected fraction of neighbors in S. So we create this bad event, which says that the neighborhood of U into S deviates a lot from its expected value. Then by turn-off, you get like some bound of what the probability is that this bad event happens. And now you can apply Lovász-Local lemma because somehow these events only depend on twice the neighborhood, like vertices at distance 2. Only these events depend and the rest doesn't depend on each other, if you think about it for a bit. So then you can show somehow that no AU will happen for some cut. And you can in fact use the quantitative or qualitative, I never know which one, which gives you a lower bound on the probability that actually no such A sub U happens. And then we can argue that actually also S has the expected value. And like if you have these two probabilities, you have to sort them the right way around so that both happen simultaneously.
Somehow LLL is taking care of, I mean, morally speaking, most of the events are like mostly independent, but they're actually not. And so that's why Lovász-Local lemma helps you.
Yes.
Okay.
Yes, Susan.
I was going to ask, is this where you said that you got a very large D?
Yes, 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 yeah, exactly. But like here we need a turn-off, right? So this only holds for D large enough. And then you want this probability to be small enough so you can apply LLL. And therefore you get a large degree. But again, like, yeah, I am too lazy to optimize these parameters. It could be that just, yeah, but I don't think you can do a lot. Try if you feel like it. I don't have the energy to do it. Okay, good. So we have this C-epsilon degree balance cut in every deregular graph. And now the next part is to show that such a C-epsilon degree balance cut actually satisfies all these properties. And now I was very mean and I was a bit lazy and I just copied the entire statement from the paper. So let us try to make sense of this. So we have like these constants C, epsilon, and D. Let's not worry about it too much. C has to be fairly large, so S has to be rather big, so that you still have control over the spectrum of G of S. Like you always want to maintain the spectrum, like control over the spectrum. So therefore, C has to be fairly large. You have some, again, some lower bound on D, but this is not as bad as from the previous lemma. Yeah, so we have n odd, we sample G, and then for any degree balance cut, it holds that G is maximum degree robust. G is also odd cycle robust. It's an G of T is an alpha expander, and G minus U has a perfect matching. Good. I mean, it's the same as before now, just like with all the dependencies. Do you want me to explain it in more detail, or I'm perfectly fine just ignoring how everything depends on each other?
It depends on what we need to know. But S was the part where you got a C fraction of the neighbors. But then I guess the T is also like if you get a balanced set of edges into S, then you have a balanced set of edges into T also, I guess.
Yes. Right. And each vertex has like roughly a C fraction of the edges into S. Good.
And what is it about S that may like, yeah, I guess one, like, why can't I, what's special about S here? It's probably was somewhere in the previous, like, you know, how do I distinguish S from T?
S comes before T in the degree balanced cut. yeah, sorry. Yeah.
No, but S is slightly larger than T, for instance, right?
Yes.
So I guess my question is, do you know from the previous definitions, you know some things about S that you don't know about T, or no?
Not really. I mean, S is of size C times N, T is of size 1 minus C times N, plus minus this epsilon N. That's all.
And you just know that the degree distribution is somewhat even.
Yes.
And then you say, hey, let's embed my graph in the S and T look really, really the same, except that S is the slightly larger one. And then we'll embed into T because, I don't know, because we like T.
No, because in the larger part, we have a better control of the spectrum. Like we can prove better bounds on the larger part. Like if you take two small subset set of vertices, then you lose control of the spectrum. You don't really know what the spectrum will look like of the induced subgraph. So you want to choose S as fairly large so that you have good control on the spectrum of G of S.
And the reason you need the spectrum is because of this matching argument in the end?
Yes, exactly.
Mm-hmm. Okay.
Good. So yeah, we can look at these different properties one after the other. So first, max degree robust. This is really a corollary of the mixing lemma, because what does the mixing lemma say? Well, it says if you look at a set U, then you get some control of the number of leaving edges, right? And then once you have control or an upper bound on the number of edges going outwards, then you have some control of how many edges you have left remaining in the set. And therefore you can show that the average degree is fairly large. And this is what we do. Okay, so we have like our set U, and the mixing lemma gives us control over how many edges are leaving. So you get an upper bound on this, and if you get an upper bound on this, you get a lower bound on how many edges you have inside, and then you get a lower bound on the average degree. And this is what we use. Good. Okay, then I'll move on.
Okay.
So the second part is to like show that we have like this odd cycle robustness. So what this mean? This meant that we look at graphs of size like 4 over square root d times n, at least this large subgraphs, and we want that L is a lower bound on the length of an odd cycle, and the upper bound is 2 times diameter plus 1. So good. Okay. Good. So there is a known result by Lovász, which says that the number of I cycles of length I, are asymptotically independent Poisson random variables with this mean. Okay. And then you can use concentration bounds to show that you don't have too many cycles of length at most L. So I mean, I just said like, yeah, no more than log n many of these. So these are really few, right? They are all constant length. So you have only like L times log n many vertices in these short cycles. And we also know that subsets of size like 3n over square root d induce a non-bipartite graph. And you can either again see this using the mixing lemma or Hoffman's bound, which gives a bound on the size of independent sets in spectral expanders. Okay. So, but once, I mean, you have these two statements, then clearly if you go into a bit larger graphs, that is 3n over square root t, and before n over square root t, you can remove all short cycles, right? And you know that this is still a non-bipartite graph, and therefore there has to be an odd length cycle, which now is of length at least L, because you removed all short cycles. And then the upper bound, it's really silly. Like suppose you don't have any odd cycles of length at most L. Well, we know that it's still expanding, right? So you can actually find that like if it's longer than 2 times the diameter of G, you can actually find the path that makes the cycle shorter. And then either like this part is odd or this part is odd. So then you can just reduce it further. And you get the upper one. Good. So more clear what's happening.
Can you go back on the previous slide just a second?
Yeah, sure.
So this you said holds for any kappa.
And maybe
U
is there for any
U is a
kappa?
subset of G.
Yes. Yes. So U is a subset of the vertices in G. And it's at least of size kappa n, right? It's linear in n.
But D is constant.
D is constant, yes.
The degree of the graph is constant.
Yes.
So in particular, you have an independent set of size linear in the number of vertices. Like you just take one vertex, remove all its neighbors, now take another vertex, remove all its neighbors.
Yes, so you have an independent set of size 1 over D, I guess.
Yeah. So
And yeah, so if kappa is equal to 1 over D, then this is
what you get
D.
here is going to be,
This is 1 minus something. So I don't think it gives you anything.
so whatever you get here is going to be too bad. That's what you're saying.
Yes.
Okay, so you're going to use this for some kappa that's actually bounded away from 0. That's larger than 1 over D. Like the kappa you're going to choose is going to be.
Yeah, I think it's going to be like 1 over square root D, I think.
Okay. Okay. Sorry, I was just trying to make sense out of this.
No, sure, that's fine. Yeah. Okay.
Okay, thanks.
Oh, okay, good. Yeah, so do you have questions about this odd cycle robustness? I think the bottom line is like look at Lovász book and you'll find the results. Like, yeah. Good. Then the third part is that G of T is an alpha expander. So here you just use 2 theorems from linear algebra, Wales theorem and Cauchy's interlacing theorem, which gives you control over the spectrum of G of T. And then you get an upper bound on the second eigenvalue of the adjacency matrix, and therefore you have spectral expansion. Nothing happening. Good. I mean, if you want me to, I can tell you what Wales theorem is and what Cauchy's interlacing theorem is. But yeah.
Can you say something briefly, perhaps? Or is it just, or it's not very informative?
It really is just apply these theorems and you get the statement. I don't have further intuition. I don't know. I mean, I'm happy to write it out if you want me to.
But what would you be worried about? I mean, you know, so the graph we started with, G, was random, was it?
Yes.
So it was probably a great expander.
Yes.
But now, for some other reasons, we're cutting up the graph in roughly, well, 2 parts, and this is the slightly smaller part. So what you're worrying about now is that the cut happened so, it was such a bad partition in some way that G induced over T like lost the great expansion it had before.
Yes, exactly.
And then what do these theorems say? Do they say, no, don't worry, regardless of how?
Basically say if you have control over the minimum degree and the maximum degree, so this is somehow a reason why you have these degree balance cuts, right? So if you can have control over these, then you can get bounds on the spectrum of, or yeah, you can get bounds of each eigenvalue. Yeah.
But you never need to throw away. I mean, it's also, I mean, you could imagine like, okay, if you had a few isolated vertices where somehow the degree was screwed up, you could imagine having some, you mentioned about closure before, then somehow what closure would do, it would take care of these bad vertices separately and restore expansion on the left. But
yes.
Here you're not willing to drop S, and you're not dropping a single vertex when you're moving to S and T.
No.
Okay.
But the reason why we can do this is because we have control of the degrees. Okay, and then the fourth, and I'm sure you're very excited about this one, and you thought that a lot is going to happen, but basically there is this theorem that says if you have again control over the maximum eigenvalue of the Lagrangian. So right, let's see. So we have diagonal matrix, which is all D, and we subtract the adjacency matrix of G. So then we get the Lagrangian. And we look, so right in here, like the interesting eigenvalues are the largest ones, and here the smallest ones are the interesting ones. Okay. So if you can bound the largest eigenvalue of the Lagrangian, so this is like the notion of bipartiteness, how bipartite the graph is, right? If I didn't mess this up. Yeah, I think this is right. And here by the second smallest eigenvalue of the Lagrangian. So this is somehow in the adjacency matrix for all, this is the number that ensures that we have good expansion, right? So if we can say that that you get this relation, then G actually has a perfect matching. Okay. And now again, like G minus U, where U is now an odd-sized subset of the set T, right? Let me just draw a graph. So we have G, we have S, and we have T, which is drawn wrong because it's more like this. And we have U here of odd size. So we remove U from the graph. Then what I claim is that, again, we have good control of the spectrum G minus U, in particular because we know that the minimum degree of each vertex is at least C times N minus epsilon times N, right? This is by this degree balance cut. Because you have this, then you can apply again Wales theorem plus Cauchy's interlace theorem to get good control of the spectrum, and then you can actually show that you can apply this here.
I'm thinking now I should know this, but how do the eigenvalues of the Lagrangian relate to those of the matrix? So there's no normalization because the graphs are regular, right? So L min plus 1 is the second smallest of the Lagrangian, and that is exactly this, like the second largest of the adjacency matrix. I guess. And the Lagrangian always has eigenvalues 0. And then the second after 0, the gap between these two is a measure of the expansion. Is that right?
Yes.
Okay. But what is L max? So L max would be, for instance, suppose that the graph is in fact bipartite. So what is L lambda max then?
So in the adjacency matrix, it would be minus D, I think, right?
Yeah.
And now it's...
Is it like 2?
Yes,
Or,
I think it's 2.
Or 2D,
This is right.
depending on the... I guess we're not normalizing,
Then
so I guess
2D,
it's
yeah.
2D. So in particular, like if the graph is very close to bipartite, then we would expect this inequality to fail badly.
Yes.
Mm-hmm.
Yes.
Okay.
Yeah, but I mean, we already know that like a constant over square root d fraction of the vertices are non-bipartite, right? So therefore you somehow can apply this. And yeah. Yeah, so this is all there is to the partition lemma. Good. Do you have enough? Do you want me to tell you something more, or?
About your favorite lemma?
Thanks for asking. Yeah. So what is actually the problem? So the problem is that we have this not too long odd length cycle, and clearly we can connect this to one of the branches, right? Just because like we have expansion. Yeah. Is it clear where we are? Like, right, we want to connect like this vertex embedding with this vertex embedding, and we can clearly like connect it on one side, like to this cycle, right? Because G of C is expanding. So now we have like this neighborhood of this branch here, which is fairly large. And we want to find a path that is vertex disjoint from this path, from the original path, connecting it to the other vertex embedding, right?
Sorry, I got lost. Can you say what we're doing again?
So we let's assume that we have a path P to the cycle C, connecting like this edge embedding to this cycle, right? And now what we would also like to find is a path Q connecting this other vertex embedding with this short cycle. But Q and P should be vertex disjoint, right? If they intersect, then we cannot do this argument of, oh, you can actually switch the parity. Okay. So what you want to find is a path from C to the neighborhood of this branch here. It's called a set U. So clearly, if C is very large, like much larger than the path P, then this is very easy. Because then by expansion, you will somehow get vertices that are not on this path P by like growing this, like by looking at the neighborhood of your cycle C, going one distance further and further and further. Do you understand what I mean? Kind of. I mean, the worst thing that could happen is somehow that C only has neighbors on this path P, right? That would be terrible. Because how would we connect it then to the set U without crossing the path P? So what we want to do is somehow we want to like look at all like short paths from C that intersect P and like create this onion-like structure, right? Like keep on going until our set here is large enough so that we can apply expansion to this set. And even if we remove the entire set P, the path P, then we still have expansion, right? So that there are vertices outside the path P that have to be neighbors, right? Well, once it grows large enough. So then once you have this, then you can somehow just by expansion find a path to this set U. Okay. And then because you have this onion-like structure, you can actually like fiddle with the paths so that you actually get two paths that are vertices joined and connect to the cycle C. So you have like this onion-like structure that you then like have to unravel. I don't know. I really like this argument. Yeah.
So the idea is that you want to grow this set of your onion large enough so that you can apply expansion. That's the idea behind it. Okay.
Yes, exactly. And you grow it by like taking like short paths that intersect the path P. Okay. And then because this part is like too connected to your cycle, right? Mm-hmm. Then like even if you have like two paths connecting to this thing, you actually get vertices joined there.
Okay. Mm-hmm.
Like paths.
Apart from expansion, what else do you use? Like the initial cycle is large enough or something like that, or?
Yes, you need to assume that the initial cycle is at least like size 1 over alpha plus 1, I guess. So that like this, like the first vertex here on P is not your only neighbor. Or I mean plus epsilon if you want.
Is to start building the onion or something like that?
Yes, exactly. So yeah, the length of the cycle should be larger than this. And then you want the upper bound on the cycle C in order to ensure that your embedding of the edge is not too large, right? You always have to ensure that the embedding is small enough. So that's the reason why you need an upper bound.
But these paths that you're creating, P and Q, might they not be too large?
No.
Or by expansion, it's not?
Yeah, you can bound them.
Okay.
Yeah. But like the cool thing I think is that like if you generalize this this argument, you can say that you could take like a set U. Like this has nothing to do with the paper. It's just a cool statement that so you have two sets U and V, and all of like both of them, let's say they're like of size log n. And the size of V is roughly log n. And then you want to have like some alpha larger. Then you can actually show that you can find paths from U to V, so that every vertex in U has an outgoing path to V, and the length of all these paths is bounded by log n. I think this is super cool. I have no idea what to do with it.
So can you say that again? So from every vertex in U, so you have what, U union V is an expander or something?
No. Like we are in a graph G on n vertices, and it's alpha expanding.
Okay.
Alpha expander. And then you look at two subsets of vertices. They're both of size log n. U and V is like slightly larger, like it has like some alpha squared over log n, or alpha over, I don't remember. Then you make it a bit larger. Then you can show that you can find paths, vertex disjoint paths from U to V, so that every vertex in U is in one path, right? And the length of all these paths is bounded by log n. So it's a constant times log n long. Let's say log squared n, because there should, yeah, let's say log squared n, but like polylog n. I don't know. I think this is.
And do you use this, or is this
No, this is way too general. But you can prove this. Yeah. It's just a fun statement. Yeah, I don't know. I don't want to bother you with other thoughts. Yeah. Or do you want me to say?
Use for the other formula, the even coloring or whatever.
Yes.
What is that the same idea? I got.
So there you use another idea called I forgot, but what you can let's just draw here because I have some white space. What you can show is that a graph G and D is like equivalent to choosing you take Gn2 and then the disjoint union of these. I guess I should draw this different. So you take random graphs where each vertex has degree 2, and then like possibly like plus like some Gn3, but let's assume D is even. So you can think of it as taking regular random graphs, each of degree 2, and then you condition on the fact that these are disjoint, and you take the union of these. So then you can show that G and D behaves kind of like this, like with high probability. So then you can like partition your two regular random graphs into two sets, right? On one set, you're going to run this perfect matching lower bound, and the other set you're going to use to somehow set enough edges incident to every vertex to 1, right? So let's see whether I get this right. So you can partition the graph G. Let's just do like 4 vertices and like this, plus we have too few vertices, but you get somehow like edge disjoint graphs, like 2 of them, each of this one of degree D over 2 minus 1, and this one of degree D over 2 plus 1. Now on here, you want to run the perfect matching lower bound. And here you can just take Eulerian paths and set every other edge to 1, right? I fear I messed up the degrees. But if you do this the right way, then each vertex will sum to the correct number of edges incident. And so then you can again hit it with a restriction and you're left with the perfect matching.
This also holds for bounded Frege. The size of
Yes. 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 Oh no, you don't do every other. Sorry. There are two ways how you can prove this. No, in this way you just set all the edges to 1, right? Yeah, sorry, I got it wrong. Right. So then I chose these correct. So then you get d/2 minus 1 edges incident to every vertex are set to 1. And then from the perfect matching over here, you get +1. Yeah, sorry. Yeah, okay.
What you're saying is that somehow you can fill up with edges so that the final edge for every vertex that the even coloring wants will have to be a perfect matching.
Yes, exactly. And I mean, yeah, then you can like generalize this to G, like not just even coloring, but perfect matching, like summing to 1 to 3 to 5 to 7 or whatever. Yeah. But yeah. Yeah, that's now I think I'm really run out of ideas of what else to tell you.
Did you by any chance also think about whether, like, yeah, how you could prove this directly without going via reduction?
Yeah, like for 2 years or I don't know how long. I have no idea how to do this. Like, yeah, no, really, yeah, this is very annoying. I would like to do this without reduction, but I don't consider this proof as very pretty, but it works. Yes. I mean, I would love to have a direct argument as to why this is hard. But, yeah.
I mean, I think the proof is very nice, but it's maybe the reduction is what's losing this log n, and if you had some direct proof, you would get something better.
Yes. Yes.
Okay, thank you so much, Kilian. I don't know, any final remark or questions, comments? Otherwise, I think, I mean, it was a great presentation and especially good to get a little bit of information on what goes in under the hood, which is quite a bit, obviously. So thank you so much.
Thanks for listening and sticking around.